Hey everybody, Trey here, and welcome back to another video. Today we're going to talk about the largest and most intense tornado outbreak to ever hit the northeastern U.S., and that is the May 31st, 1985 tornado outbreak. Many of you have asked for this case study for quite some time, so we are going to tackle it today. Storms erupted from Canada into the northeastern U.S., producing a total of 44 tornadoes, well over half of which were strong to violent F2 plus tornadoes, including 8 F4s and 1 F5, which impacted places like Niles, Ohio, and Wheatland, Pennsylvania. All in all, 90 people died, 76 here in the U.S., making it the deadliest outbreak ever in the state of Pennsylvania, and second in Ohio only to April 3rd and 4th, 1974. In this video, we're going to dive into the meteorology behind the May 31st, 1985 tornado outbreak and discuss some of the reasons why it was such an anomalously significant outbreak for the region. So without further ado, let's go ahead and get started. The outbreak first began north of the border during the late afternoon hours on May 31st. Several supercells developed and tracked across southern Ontario, producing multiple significant tornadoes. Perhaps the most notable of these was the F4 that tracked through the town of Barrie. Despite only having a 6.2-mile path, the tornado damaged or destroyed 300 homes in the town of Barrie, causing 8 deaths and injuring 155. Total damages from the Barrie F4 added up to 150 million Canadian dollars back then, which is equivalent to 374 million Canadian dollars today. To its south, another cyclic supercell spawned an F4, which remains the longest tracked Canadian tornado to date. Its path totaled 62 miles in length, with some sources saying that it may have been over 70 miles in length, and it produced significant F4 damage in the town of Grand Valley. The Canadian activity was well underway by the time the outbreak began on the U.S. side. The first in a series of strong to violent tornadoes began around 5 p.m. Eastern Time in far northeast Ohio, tracking into far northwest Pennsylvania. The tornado most notably tore through the town of Albion, Pennsylvania, where 9 people died. The F4 leveled a 2-block by 10-block area in town, destroying a total of 309 buildings. Several violent tornadoes followed, including a long-track F4 that began in Trumbull County, Ohio, near the Ohio-Pennsylvania border, and tracked into western Pennsylvania, carving a 56.2-mile path through both states. The tornado killed 5 in Atlantic, Pennsylvania, where a grain mill and chair factory, among other buildings, were completely destroyed. An additional 5 were killed at a trailer park in Cherry Tree, Pennsylvania. The same storm that spawned the Albion tornado spawned 2 others, including an F4 that tracked through Corry, Pennsylvania, before dissipating in rural western New York. A farm was completely leveled with nothing but a silo left standing, and eyewitnesses claim that they saw the entire farmhouse airborne. Another F4 tracked through the Moshannon State Forest in Pennsylvania, tearing an over 70-mile-long path through complex terrain. The tornado was over a mile wide at times, with some reports suggesting it was nearly 2 miles wide at times. The F4 downed an estimated 88,000 trees, becoming the longest-tracked tornado of the outbreak. An F3 tornado tracked north of Pittsburgh through Beaver and Butler County. In the town of Beaver Falls, a shopping center was destroyed, where 2 people died. The most intense tornado of the outbreak was the Niles-Wheatland F5, which cut a 47-mile-long path through eastern Ohio and western Pennsylvania. It began near Newton Falls, Ohio, where 400 homes were heavily damaged or destroyed at F3 to F4 intensity. The tornado intensified into an F5 as it moved into the town of Niles, Ohio. Here, hundreds of homes were destroyed, several of which were swept away despite having anchor bolts, with their debris scattered downwind. The Niles Park Plaza shopping center was completely leveled and partially swept away as well. And at an industrial area that was hit, large 30-foot-tall metal petroleum storage tanks, each weighing 75,000 pounds, were torn from where they were anchored and tossed considerable distances, some of which bounced several times over their journey. As the tornado crossed the Pennsylvania state line, it demolished the town of Wheatland, where a trucking plant was pushed off its foundation and leveled. Pavement was scoured from parking lots as well. 95% of Wheatland's business and residential areas were destroyed. All in all, 18 people were killed, 310 were injured, and it remains the only F5 ever to occur in Pennsylvania and the farthest east F5 or EF5 in U.S. history. Before we move on, I wanted to remind you about my new site, stormchasercoaching.com. Here, you can find the most in-depth educational content specifically tailored to help you improve your storm chasing skills, created by some of the best storm chasers and meteorologists in the world. If you're someone who wants to start your storm chasing journey safely and effectively, or you're a veteran chaser who wants to improve your game, Storm Chaser Coaching is for you. Join our free community to connect with like-minded weather enthusiasts and storm chasers, and if you're ready to level up your storm chasing, subscribe to our Chaser Academy for our entire content library, including our in-depth educational modules, unique Chase and Explain videos, and much more for less than the cost of a tank of gas each month. For more information, visit stormchasercoaching.com today. Thanks so much. Now back to the video. All right, let's dive into the meteorology behind the May 31st, 1985 outbreak. We'll start out at 500 millibars like we always do. The brown lines are your geopotential height contours. The blue lines are your isotax or wind speed contours. And of course, the wind barbs are plotted in blue as well. We'll start out a couple of days before the May 31st outbreak took place on May 29th. You could easily see the trough that was going to eventually be responsible for the May 31st outbreak, and it was this one taking up much of the western U.S. Fairly high amplitude trough with some strong winds surrounding the base of that trough. That would stay intact for quite some time as it traversed the U.S. You see it digs down a little bit more and then ejects off to the east into the plains on May 30th. Actually spawned quite a bit of tornadic activity on May 30th. We had some tornadoes during the day from the Dakotas into Minnesota and Montana. And then during the evening hours, the trough, as it ejected off to the east, produced some activity across Minnesota, Iowa, down toward the Kansas City area. And then a supercell occurred after dark that produced multiple significant tornadoes, including an F3 near Elkader, Iowa, that tracked into Wisconsin. So some pretty significant activity as kind of the day before the day on May 30th into the early morning hours of May 31st. And then the trough continued to eject off to the east, remained intact by 12Z, 7 a.m. Central Time, 8 a.m. Eastern Time on May 31st. We had a very well-defined, potent trough. You see about 90 knots of flow there at the base of that trough, at the core of that jet streak. Nice neutrally to slightly negatively tilted trough. If we were to draw the axis of that trough down the center, it would be slightly negatively tilted, but a very potent trough nonetheless, and it continued to eject off to the east during the day into the Great Lakes region by mid-afternoon, and right at the leading edge of that jet streak by mid to late afternoon was where our activity began from southern Ontario into the Lake Erie vicinity. As we've discussed many times here on the channel in the past year or so, the advent of the Omega project, headed by Chris Broyles of the Storm Prediction Center, has really enlightened the fact that the translation speed of the 500 millibar jet is a critical factor in determining whether or not setups are favorable or will be favorable for a significant tornado outbreak. So let's see how the 500 millibar jet on the May 31st, 1985 outbreak fits into that research. So the process to determine the translation speed of the 500 millibar jet is to find the centroid of the jet at 6Z, which is, again, the evening before the event. So if we were to look at the very center of the jet streak here, right at the middle of that 70-knot contour, looks like it's going to be somewhere right in there, right on the Iowa-Nebraska border, right in there. Then we go forward 18 hours to 0Z, the evening of the event, take the centroid of the jet at that point, which looks like it's going to be perhaps somewhere right here on the western fringes of Lake Erie, maybe right in there. That looks like a good centroid of that 70-knot contour there as well. So we find those two midpoints, then we find the distance between those 2 points. So let's go ahead and plot those on RadarScope here. RadarScope has that nice distance measuring tool that we can use. So we're going to start at the first point, which is right around the Sioux City area, and then we're going to go all the way to our second point, our end point for the 0Z centroid. And it looks to be right about there, right on the western or southwestern shores of Lake Erie. That's right about 700 miles on the nose. So then we take that number, 700 miles, divided by that 18-hour period, 6Z to 0Z, that's an 18-hour period, to come up with our translation speed. So let me pull up the calculator here. 700 divided by 18 gives us a translation speed of about 39 miles per hour. Now let's translate that into knots. So we'll take 39 miles per hour to knots. And that gives us a jet translation speed of about 34 knots. That is well below the threshold determined by the Omega project team. They found that jet translation speeds greater than or equal to about 40 knots. That tends to be the threshold for determining whether or not a setup is favorable for significant tornadic activity. Jet streaks translating up at a speed above 40 knots tend to be more favorable for significant tornado outbreaks than jet streaks that translate at a speed below 40 knots. And you can see that that 34 knots for the May 31st, 1985 case is well below that 40 knot threshold. So that begs the question, our jet here was not all that fast moving, but we were still able to get a significant tornado outbreak. Why was that the case? The key here was the location of the jet relative to the outbreak area. The Omega team has found that when the jet translation speed is below that 40 knot threshold, the location of the jet with respect to the outbreak area is a critical factor. And so you can see with the May 31st, 1985 outbreak, as the jet ejected off to the east into the Great Lakes region, those tornadoes happened, the outbreak area was right on the nose of that 500 millibar jet. So we were in very close proximity to the actual jet. Here it is at 0Z, even more so overlapping the outbreak area. All those tracks there are the tornado tracks. So the 500 millibar jet in the May 31st case was in very close proximity to your outbreak area, helping negate the fact that the jet translation speed was a bit slower than what we'd like to see. Compare that to a case like May 20th, 2019. This was the expected high-risk tornado outbreak in southwest Oklahoma and northwest Texas that didn't end up materializing as expected. Forecasters thought there were going to be multiple rounds of significant long-track tornadic supercells across southwest Oklahoma and northwest Texas, and instead we got mostly just a QLCS tornado threat with embedded circulations. Now, on May 20th, 2019, the jet translation speed was only 33.5 knots. Pretty slow, definitely below that 40 knot threshold, and fairly comparable to our May 31st, 1985 case. But watch where the location of the jet was. Starting at 6Z, the axis of the trough was still well back here across Nevada into California, with most of the strongest winds relegated to the backside of the trough. A little bit of a jet streak here across Arizona, New Mexico, into western Mexico, but overall most of that energy on the backside of the trough axis. We go forward in time into the daytime hours, and we go to about 2021Z when the outbreak was expected to kick off, and you see that still the axis of the trough is way back here across Utah into Arizona, with most of the jet energy still well back here, just getting into maybe West Texas, New Mexico area, with a little bit of stronger flow here across Oklahoma, but the majority of the trough still well back here to the west, especially far west compared to where our outbreak area was expected to be. Much different from our May 31st, 1985 case, in which our jet streak was basically right on top of our expected outbreak area despite the slow translation speed. Heading up to 300 millibars, we had quite the strong jet streak accompanying the trough, 120 knots of flow at the core of the jet streak. We also had quite a bit of defluence in the exit region of the trough. Defluence is that spreading apart of the wind vectors in the upper levels of the atmosphere, and that creates a void that Mother Nature fills by lifting air from below, and that's how you get rising motion for initiation of storms in a severe weather event. You see here over the upper peninsula of Michigan, here at 12Z, winds out of the south-southwest with almost due westerly flow over Indiana and Ohio, so very notable spreading apart of those wind vectors with height, and that would spread its way east, impinging upon the southern Ontario vicinity and then down into the Lake Erie vicinity, Ohio and Pennsylvania, during the mid to late afternoon hours. We see here as we go through the day that jet streak translates off to the east pretty quickly. And then by 21Z, very strong defluence across parts of southern Ontario into the northeast. Plenty of defluence in that exit region of the trough. And you can see here clearly as well, if we were to outline our four quadrants of our jet streak here, just doing a rough estimate around the core of the jet streak, we're splitting that up into our four quadrants. Definitely that southern Ontario portion of the outbreak in the left exit region. The Ohio-Pennsylvania portion kind of right on the line between the left and right exit regions, but with a somewhat curved jet streak here, at least a slightly curved jet streak. Some of that rising motion that is optimally in that left exit region can bleed into the right exit region. So bottom line is that we were in the exit region of this jet streak. Plenty of defluence aloft to support rising motion for robust severe storm development by mid to late afternoon. Let's head down to the surface now. We'll start a couple of days before the event on the 29th. As that mid and upper level trough began to traverse the higher terrain of the Rockies, we started to see pretty significant surface cyclogenesis on the east side of the Rockies, particularly in that Montana-Wyoming vicinity by the evening of May 29th. Over the coming day, we saw that low meander its way off to the east a little bit. It remained a fairly broad low through much of the day. On the 30th, you can see at 12Z, 7 a.m. Central Daylight Time on May 30th, we just had a big, broad surface cyclone there spanning basically the southern Canada region all the way down into the southern plains with a couple of different possible centers scattered within the cyclone. But as we went through the day on the 30th, that surface low started to really deepen in earnest by the evening, and we saw much of the tornadic activity that occurred on the 30th happen in fairly close proximity to the center of the surface low, which by the evening was located along the South Dakota-Minnesota border. You see all those reports from southern Minnesota and Iowa down into the Kansas City region, fairly close to the center of the surface low, and then that tornadic supercell that occurred across northeast Iowa into southwest Wisconsin occurred just on the southeast flank of the surface low during the evening hours. The deepening continued into the overnight hours of the 30th into the morning of the 31st. By the morning of May 31st at 12Z, 7 a.m. Central, 8 a.m. Eastern, we saw, at least from this map here, the surface low down into the upper 980s as far as surface pressure goes. So that low had really deepened considerably through the day on the 30th into the 31st. Zooming in a little bit at 12Z on May 31st, we can see a pretty complex surface pattern was in place. The surface low is located on the western fringes of the Upper Peninsula of Michigan, western Lake Superior, somewhere in that vicinity there. By this time, the surface low had started to occlude, meaning that the cold front had started to catch up to the warm front, pushing all the warm air up off the surface. Now, it's very difficult to pick out occluded fronts in most cases on surface maps. I think it's somewhere in this vicinity here. Notice how there's a little bit of a wind shift across the boundary, more southwesterly flow on the west side, more south-southwesterly flow on the east side, but there's not really a strong temperature gradient across the boundary. Temperatures are in the low to mid 60s on both sides of the boundary there, but there's still a little bit of a pressure tongue. That indicates that there may be a little bit of an occluded front right there. Extending south of the occluded front is our cold front. We can draw that through the pressure tongue there, down into the mid-south and southern plains. There's a clear pressure tongue, clear wind shift across the boundary as well. Winds on the west side of the boundary out of the west across Iowa, Illinois, and Wisconsin. Much more southwesterly flow across Indiana and Ohio. Now, our warm front is a bit tricky to place, but it looks like it's draped down to the southeast from the occlusion point down through this pressure tongue here across the Midwest into the Appalachians, down into the eastern seaboard region. The temperature gradient across the boundary is not all that strong, but we do see a little bit of a wind shift, more southwesterly flow in the warm sector. On the cool side of the front, much more southerly flow. So it's a little bit tricky, but there is a bit of a pressure tongue there, a little bit of a wind shift that suggests that that may be where the warm front is located. There also appears to be a secondary warm front draped to the east from the surface low. Notice the pressure tongue here as well. There's also a clear wind shift from southerly winds out across the Great Lakes region to more easterly flow off to the north. Also a pretty big temperature gradient, temperatures in the 60s, the mid to upper 60s and 70s here in the Ontario vicinity, temperatures in the 50s off to the north. So there appears to be a secondary frontal zone, we'll call it a warm front here, draped through the Upper Peninsula of Michigan, through northern Michigan, off through that pressure tongue and wind shift, and then trailing off into eastern Canada off to the northeast. So a very complex surface pattern here to start the day, and that would persist through the afternoon. Robust moisture was already in place across the warm sector with dew points in the upper 60s to 70s all the way up into Indiana and Ohio, down to the southwest ahead of the cold front across the mid-south. And as the surface low moved off to the east during the day, so did the moisture. By 21Z, 4 p.m. Central Time, 5 p.m. Eastern Time, those mid to upper 60s and 70s dew points had made their way all the way up into eastern Ohio, western Pennsylvania, and western New York. You can see even a 70 dew point there in southwestern Pennsylvania. setting the stage for severe weather. By 21Z, the surface low had translated to a position east of Lake Superior. The occluded portion of the front was difficult to ascertain once again, but it looks like it's probably somewhere in this vicinity here. There does still appear to be a bit of a wind shift. Again, not much of a temperature gradient across the boundary, but it looks like it's somewhere in that vicinity there. Extending to the south from the end of the occluded front is our cold front through the pressure tongue, going through portions of Ohio down into the mid-south, the Mississippi River Valley, somewhere in that vicinity there. The cold front was, for the most part, the initiating boundary for this setup. We're going to come back to that in just a second, but you see the tornadic activity right there across northeast Ohio and northwest Pennsylvania, right ahead of the cold front. The warm front was, again, a little bit difficult to ascertain, but it looked to be somewhere in here, draped down to the southeast from our occlusion point through that pressure tongue off into the eastern seaboard region. So really not a super wide warm sector where most of the tornadic activity happened. And you'll notice that most of the Ontario activity was actually north of the warm front, but still there were plenty of ingredients to support severe weather there. Of course, the forcing from the trough, the proximity to the surface low, and we were able to get adequate moisture north of the front. Surface temperatures were a little bit cooler up here, so you didn't need as high of dew points as we did farther south. You see dew points up here in the southern Ontario vicinity in the low to mid 60s, which was plenty to support severe weather, especially with closer proximity to the forcing mechanisms. Again, down to the south, not a super wide warm sector where most of the tornadic activity happened, but wide enough to support severe weather. And because the surface low was translating quickly off to the east, that warm sector was moving with the storms, allowing those storms to stay in the warm sector for an extended period of time instead of moving out of the warm sector into more hostile conditions. Our secondary warm front appeared to be draped again through eastern Canada, through that pressure tongue up in there. Wouldn't be too much of a factor in our overall setup for May 31st, but it is an interesting feature nonetheless. And this is what things looked like by 0Z, 8 p.m. Eastern. The cold front had inched off to the east, as had the warm sector with the activity. Now, keep in mind that this is subjective analysis. This is my assessment of the surface pattern on May 31st, 1985. Multiple sources, including the weather maps that were hand-analyzed by forecasters at what is now the Weather Prediction Center, do not show this dual warm front structure. They only have a single synoptic warm front, which is our northernmost warm front draped across eastern Canada. They do not recognize the southernmost warm front that we drew from the Great Lakes down into the eastern seaboard as an actual warm front. And that is certainly plausible, given that we had quite high dew points in the low to mid 60s, well to the north of our southernmost warm front. However, I gave my reasons why I feel that there was a dual warm front structure. The location of the occluded portion of the front near the surface low and others, and also the surface analysis from the NWS at State College from May 31st, 1985 at 23Z does highlight that dual warm front structure. So as we said, it was a very complex surface pattern on May 31st, 1985. In either case, whichever surface pattern you think is correct, either were favorable for significant severe weather. Back up at 850 millibars, we had a nice low-level jet overspreading the northeast and southern Ontario during the day. It started off at 12Z as a core of 40 to 50 knot winds out of the west and northwest over the Central Plains and Midwest that translated east during the day. It did wane some in intensity as it moved off to the east, but you can see by 21Z, 4 p.m. Central, 5 p.m. Eastern, that a nice 30 to 40 knot low-level jet was in place across the Great Lakes region out of the southwest, in particular over the Ohio and Pennsylvania vicinity. And then by 0Z, that continued off to the east, 40 to 45 knots overspreading the area of interest. Let's now take a look at some soundings from across the region to see how the environment progressed throughout the day. We'll start out with the observed sounding at Pittsburgh, Pennsylvania at 12Z, 8 a.m. Eastern Time. Not a ton we can glean from this particular sounding. It does look pretty similar to a profile you might expect to see north of a warm frontal zone. Notice what appears to be a frontal inversion in the low levels of the atmosphere. Temperature and dew point go up and then veer quickly off to the right, which is fairly similar to what you'd see with a frontal inversion. Very saturated profile up to the mid-levels of the atmosphere, and your surface winds are quite backed. Pretty much east-southeasterly winds at the surface, all of which are mounting evidence to suggest that we might have actually seen that dual warm front setup like we discussed earlier. Heading down to Huntington, West Virginia, which is southwest of the Pittsburgh area, a little bit more representative of what we might see in the warm sector. Very deep moist layer, extending up to really about 700 millibars beneath a little bit of an inversion. Atop that inversion, a little bit of instability in place already at 12Z, about 900 joules per kilogram mixed layer CAPE, expected to increase going into the afternoon. And our wind profile was quite favorable for severe weather early on in the day. Even though our surface winds were quite veered, pretty much southwesterly surface winds at Huntington, we had quite a bit of veering and strengthening of those winds in the lowest levels of the atmosphere. Again, pretty much southwesterly flow at about 10 knots at the surface, veering to almost due westerly flow at 40 knots at 850 millibars, about a kilometer off the surface, leading to quite clockwise curved hodographs and strong low-level shear in excess of 330 meters squared per second squared effective storm relative helicity. Certainly a profile that would favor significant severe weather. Here is the 12Z sounding at Dayton, Ohio, in the western part of Ohio. Quite a bit of instability aloft, about 1,300 joules per kilogram of CAPE at 12Z. And I want you to notice this feature right here. This is the elevated mixed layer, and a pretty stout elevated mixed layer at that. We're going to come back to this EML in just a minute. The atmosphere quickly became more favorable for significant severe weather throughout the morning and early afternoon. A good example of that was at Barrie, Ontario, one of the cities that would be decimated by an F4 later on in the event. Now, we don't have any observed soundings from Barrie or anywhere in Ontario on May 31st, 1985, but I want to shout out my longtime viewer and supporter, Brian Bernard, who has his website, goldenhorseshoewx.ca. He has his own WRF model and is able to simulate historic severe weather cases using his WRF model, and he was nice enough to simulate the May 31st, 1985 case. I'll put a link to the output from Brian's case study on the May 31st event in the description box below. So I have a series of his WRF model soundings at Barrie, Ontario, starting at 12Z on May 31st. It looks very similar to the Pittsburgh sounding, very limited instability, not much going on, but watch how quickly things change. This is at 15Z and now 18Z, a fully destabilized profile. The model showing almost 3,000 joules per kilogram of mixed layer CAPE with a nice looking hodograph, nice clockwise curved hodograph. Certainly an environment that would favor significant severe weather. And this is again at 18Z, just 6 hours after that 12Z sounding, and we were fully destabilized. So conditions quickly became much more favorable for significant severe weather as that trough shifted into the region and as the atmosphere destabilized through the morning and afternoon. By 0Z, 8 p.m. Eastern, the event was well underway, and this is what the environment looked like at Pittsburgh. Now, I've overlaid here on the left the sounding given at the NWS State College event page for May 31st, 1985, and this is somewhat of a composite sounding. Unfortunately, the actual weather balloon that was released at Pittsburgh at 0Z popped at 500 millibars, or it had some sort of malfunction at 500 millibars. So everything you see below 500 millibars is actual observed data from the weather balloon sent up at Pittsburgh on the evening of May 31st. Everything above 500 millibars is likely from a nearby sounding. So it is a composite sounding. It's not a perfect depiction of the environment at Pittsburgh, but it's quite close, and it at least gives us a more complete look at the environment, at least the thermodynamic environment at Pittsburgh, which was almost right in the center of this outbreak. And speaking of that thermodynamic profile, it was quite impressive. Instability was quite strong with about 2,800 joules per kilogram of CAPE, and a very thick instability profile as well. Also take note at the low-level instability. 0 to 3 kilometer CAPE was about 121 joules per kilogram, so a lot of instability in the lowest levels of the atmosphere. We've talked ad nauseum on the channel here about what 0 to 3 kilometer CAPE and low-level instability can do for a tornado environment. When you have strong low-level instability, that means stronger, less impeded low-level updrafts, and that can aid in tornadogenesis in supercells, all else being favorable. Here is the 0Z Huntington, West Virginia sounding. Again, a very thick instability profile, over 3,000 joules per kilogram of mixed layer CAPE. Very strong instability, especially for this region. 83/71 at the surface, so a very moist, warm, low-level air mass, strong 0 to 3 kilometer cape. Even more than at Pittsburgh, 174 joules per kilogram, so very strong low-level instability. That likely played a role in, again, intensifying those low-level updrafts to aid in tornadogenesis in the supercells that developed. Here is Buffalo, New York. Not quite as high instability. Looks like we had another malfunction here, just above 300 millibars, but overall you can see a nice thick cape profile, strong low-level instability, and steep lapse rates aloft. So all across our area of interest, or the outbreak area in general, we had very strong instability. And a big reason why we had such strong instability across the region was that elevated mixed layer. You can see it here at Pittsburgh at 0Z, this layer of very steep lapse rates aloft. That is your elevated mixed layer. As a refresher, the elevated mixed layer, or EML, is that layer of warm, dry, well-mixed air that emanates off the higher terrain out west, western Mexico, the desert southwest, the southern Rockies, and it gets transported out east on the westerly or southwesterly mid-level flow over top of the low-level moist layer that's sitting out east in areas like the plains, the Midwest, etc. But it's very rare that such a well-defined moist layer actually makes it intact all the way up here into the Northeast and Eastern Canada like it did in the May 31st event. For one, this was a very stout elevated mixed layer for this region. The 700 to 500 millibar lapse rate at Pittsburgh at 0Z was 7.8 degrees Celsius per kilometer. Using the Storm Prediction Center's sounding climatology page and looking at every single 0Z Pittsburgh sounding going back to 1952, which is almost 55,000 soundings, this 7.8 degrees Celsius per kilometer value would rank top 40 all time for 700 to 500 millibar lapse rates at Pittsburgh at 0Z. And as far as instability goes at Pittsburgh at 0Z, that cape value was about 2,800 joules per kilogram. Now again, this is a composite sounding, so it's not a perfect representation of the instability in the environment, but it's likely very close to what the value actually was. Using that same database of nearly 55,000 soundings, that value would rank number 6 all time at 0Z at Pittsburgh for mixed layer cape. So this was quite the upper echelon thermodynamic environment for this part of the country, and it was due in part to the upper echelon intensity of the elevated mixed layer for this region. And number 2, it's extremely rare that an EML of any strength makes it intact this far northeast. This is evidenced in Figure 2 from Anderson et al. 2024. They looked at the number of what they call EML days per year across the U.S. An EML day, as they define it, is a day in which an EML that meets their criteria is present at a given location. And this particular map shows the frequency of EML days for March, April, and May put together. And you can see the plains gets on average 12, 15, 18 EML days every spring. But take a look off to the northeast, Pennsylvania and New York. They get well below 1 EML day per spring on average. So it's very rare to see any type of EML make its way all the way up into the eastern Ohio, Pennsylvania, New York region during the spring. However, the background pattern was quite favorable on May 31st, 1985 for the transport of a strong EML all the way from the source region into the northeast. Banacos and Exeter 2010 looked at the relationship between the elevated mixed layer and severe weather events in the northeast U.S. And in their Figure 4, they came up with a composite 700 millibar pattern for events that are tied to an EML in the northeast. The top panel you see here is the 700 millibar geopotential height pattern 24 hours before the event, and the bottom panel is for at the time of the event. The solid black lines that you see are the geopotential height contours at 700 millibars, and the shading represents the geopotential height anomaly at 700 millibars. The blues, purples, and pinks indicate below average geopotential heights, indicating the potential for more troughing, and the greens, yellows, oranges, and reds indicate above average geopotential heights, indicating the possibility of more ridging. And they found that there are several components that allow for EMLs to be transported into the northeast as far as the 700 millibar background pattern goes. Number one, you see a trough across the west coast. This allows for the ejection of the elevated mixed layer from the source region, again, the higher terrain out west, into areas off to the east. We then see a large anticyclone over the kind of southern half of the country that is located a little bit farther north and west than what is typical. That leads to these higher than normal heights across the Great Lakes, Midwest, into the Mid-South region that you see on the composites here. Their research showed that this anticyclone is quite necessary to provide for, number one, that westerly flow needed to transport the EML off to the northeast, but they also found that the subsidence or sinking motion from this anticyclone or ridge is a necessary component to allow the EML to remain intact as far northeast as the northeastern United States. Oftentimes, EMLs will become much more diffuse. They'll wash out due to a number of factors, including enhanced convection as the EML translates off to the northeast, and other factors. The subsidence from the high-pressure ridge allows for more limited convection and allows the elevated mixed layer to remain intact along its journey all the way into the northeast. And the third component is this shortwave trough moving across southern Canada into the Great Lakes region and northeast that allows for the EML to become entrained within it and set up over the northeast to maximize its impact on severe weather events in that region. And it provides the forcing necessary to initiate severe convection in that EML-influenced air mass. And our 700 millibar pattern leading up to the May 31st outbreak was a fairly good match for the Banachos and Exter 2010 composite. This is the 700 millibar map starting at 0Z, the evening before the outbreak. The brown lines, again, are your geopotential height contours. The blue lines are your isotachs or wind speed contours. The wind barbs are in blue as well. And the dashed red lines are your 700 millibar temperature. So you can kind of see the thicker dashed lines are your warmer 700 millibar temperatures, which would be associated with your elevated mixed layer. So you can kind of see it track northeastward as we go through this loop here. Starting the evening before the event, and even before that, we had the skeletal components in place matching our Banachos and Exter composite. You see a fairly large ridge located here across the southern tier of the country. It wasn't quite expanding as far north as in many of the cases that Banachos and Exter looked at, but it did extend quite a bit farther west, all the way into western Mexico and the desert southwest. You see the height contours bowing upward here over that region. So a pretty far westward expansion of the anticyclone or ridge helped favor that EML transport off to the northeast. And then, of course, our trough that we talked about earlier. Our main driving factor for this outbreak synoptically was this trough. Fairly deep digging trough, perhaps the reason why the ridge was a little bit more suppressed than in some of the other cases that Banachos and Exter looked at, but a very deep digging trough allowing the EML to be kind of picked up in between that ridge and this trough. That westerly mid-level flow allowed for the transport of the elevated mixed layer off to the east and northeast, and then as the trough intensified going into the day on May 31st, again, that ridge was quite expansive off to the west, and we had that trough that was able to entrain the elevated mixed layer into it. You see the dashed red contours all the way up into New York and Pennsylvania. Some of that warmer 700 millibar air was able to entrain that elevated mixed layer into the trough, and of course, we had plenty of forcing for severe convection in that elevated mixed layer influenced environment, which, as we talked about earlier, was quite unstable and favorable for significant severe weather. Farrell Jr. 1988 performed a backwards trajectory analysis to try to trace the origins of the elevated mixed layer. So what he did was take the elevated mixed layer air over Dayton, Ohio at 12Z, the sounding that we saw earlier, and he tried to trace it back to see where it came from. And he actually found that the elevated mixed layer responsible for the May 31st outbreak originated at least 2 days earlier in northeast New Mexico. It then got picked up by the trough, trekked all the way over the central U.S. and into the Ohio-Pennsylvania vicinity. Unfortunately, I wasn't able to obtain an Albuquerque or Amarillo sounding, which would have been closer to that northeast New Mexico source region, but here's a sounding from Midland, Texas in West Texas on the evening of May 29th, so 2 days before the outbreak, and you can see this very deep layer of extremely steep lapse rates and well-mixed air, emanating up from the surface to almost 500 millibars. That is a very deep layer of steep lapse rates and well-mixed air aloft, indicative of your elevated mixed layer. We move on to Little Rock, Arkansas at 12Z the following morning, so the morning before the event on May 30th, and you can see evidence of that elevated mixed layer between about 700 and 500 millibars. That layer of steep lapse rates right there is your elevated mixed layer, so clear evidence that it's translating off to the northeast from its source region. And then we go to the morning of the event, 12Z on May 31st at Dayton, Ohio. We've already seen this sounding, but very clear evidence of your elevated mixed layer in the mid-levels of the atmosphere, that steep lapse rate layer there. And it continued to translate off to the northeast through the day into our area of interest where the outbreak occurred. This is the 0Z Pittsburgh sounding from the evening of the event, and a very clear depiction of that elevated mixed layer in the mid-levels of the atmosphere. And Farrell Jr., 1988, even said that the lid, as he called it, the elevated mixed layer, even made it as far northeast as Maine, which is extremely rare. And finally, here's a bit of a visualization of the mid-level lapse rate plume indicative of the elevated mixed layer using Brian Bernard's WRF simulation of the May 31st event. This shows 700 to 500 millibar lapse rates starting at 6Z on May 31st, so the early morning hours of May 31st. And you'll see the lapse rate plume indicating the elevated mixed layer. It's that shaded region there that shows 8 degrees Celsius per kilometer lapse rates. Starts to overspread southern Ontario into Ohio by late morning to early afternoon, and continues to spread off to the east during the day into eastern Ohio, western Pennsylvania, western New York, through the afternoon and evening of the event, setting the stage for significant severe weather. So it's quite clear that the anomalously strong and well-defined elevated mixed layer for this region was a critical part of why the May 31st event became what it became. To have such a strong elevated mixed layer remain intact, spread over the area of interest during the day, created a truly rare thermodynamic profile for this region, and no doubt allowed for explosive convective development. And when you couple it with this kind of a shear profile, you get a volatile combination of ingredients that favors significant tornadic supercells. Take a look at the hodograph here off to the right. Your low-level hodograph, nice and clockwise curved, even though the surface winds are quite veered. Oftentimes we talk about the fact that winds often need to be out of the south or southeast to have a better shot at storms producing tornadoes in a given environment. Well, these winds were quite veered out of the southwest at about 10 knots at the surface, but sometimes it just doesn't matter when you have strong veering and strengthening of the winds with height in the lowest kilometer or two. You see here those winds at the surface about 10 knots out of the southwest, veering to almost due westerly at 50 knots about a kilometer or two off the surface. So strong veering and strengthening of the winds with height despite veered surface winds, and that creates that nice curved hodograph that you need for significant tornadic supercells. Here is the evening sounding from May 31st at Huntington, West Virginia. Once again, extremely high-end thermodynamic profile for this region. Strong low-level instability, strong deep layer instability coupled with this kind of a shear profile. Again, strong turning of those low-level winds with height, leading to almost 200 meters squared per second squared effective storm relative helicity, likely a bit larger at Pittsburgh, and strong deep layer shear. Notice how lengthy the hodograph is. Deep layer shear at about 50 to 60 knots there. Plenty of shear to favor organized convection, including supercells, that would explosively develop in this kind of a thermodynamic environment. And finally, here's the Buffalo, New York sounding. Once again, plenty of instability coupled with a very favorable looking hodograph there. Strong low-level winds, even though the cold front had started to overtake Buffalo by this point. So you had a little bit of a wonky west-northwesterly surface wind, but still plenty of curvature in the low levels of the hodograph, leading to in excess of 350 meters squared per second squared effective storm relative helicity. So all in all, a very volatile combination of ingredients, a very Great Plains-like combination of ingredients that favored significant tornadic supercells over a broad area in this outbreak. Storms first initiated in southern Ontario, just east of Lake Huron, as you see in this visible satellite imagery. They appear to have developed along the frontal zone, perhaps with some influence from a lake breeze convergence boundary. Perhaps when the front crossed into southern Ontario, it collided with a lake breeze convergence boundary off of Lake Huron, initiating storms where that collision occurred. Not quite sure if this was actually the case, but some sources do cite the lake breeze boundary as being a player in the southern Ontario supercells. Skies were also free and clear of antecedent convection thanks to the elevated mixed layer. Those storms developed between 18 and 19Z, and shortly before 20Z, storms then developed in northeast Ohio, apparently along a prefrontal confluence band. Notice the cumulonimbus clouds along a confluence band right there. The cold front was well back here along the boundary between the clear skies to the west and the cumulus to the east. So this was clearly a prefrontal confluence band that initiated the first round of tornadic supercells in this event. Now, it's very difficult to tell using the surface maps that we have from this day. This is the WPC hand-analyzed map from that day at 21Z. Just after storm initiation, your cold front is right in here as they have analyzed it. And here's Ohio, and you do see perhaps a little bit of confluence just ahead of the cold front. Winds just ahead of the front, out of the southwest, a little bit more southerly flow just off to the east. So perhaps a very subtle confluence boundary right in there coming off of Lake Erie that may have initiated that first round of tornadic supercells. If we back the loop up to the beginning, you can even see that agitated line of cumulus right in here, well ahead of the cold front, which was again back in here somewhere. And this was good, clear evidence that we had a confluence band in the open warm sector well ahead of the cold front. Storms developed on that just before 20Z. They moved from northeast Ohio into northwest Pennsylvania, and that was our first round of significant to violent tornadic supercells. And then the cold front, which again is that boundary between the cloud-free skies to the west and the cumulus clouds to the east. Storms then developed along the cold front after 21Z, and that was our second round of tornadic supercells in this event. Like the other storms, they too explosively developed into supercells and quickly became tornadic. There was also a little bit of open warm sector activity even out ahead of the prefrontal confluence band. You see a couple of cumulonimbus clouds out in here in eastern Ohio. Those would struggle for quite a while, perhaps due to the capping over the warm sector and weak forcing in that region away from the confluence band, but one of those eventually did percolate a little bit more. It was this one here that moved into northern Pennsylvania and became a significant tornadic supercell itself. You can see how robust it got in the visible satellite imagery here. Now, notice how discrete the storm mode remained in this event despite the cold front initiating the bulk of the convection. You can see the individual updrafts here in this satellite image, very discrete updrafts along the cold front. And we've talked before how cold fronts tend to be fairly messy in these storms that they initiate. But that was not the case here. First off, if we were to draw in our cold front on this map of 0 to 6 kilometer shear vectors, so our deep layer shear vectors, you'll notice that our deep layer shear vectors are quite perpendicular to the cold front, which, as we've talked about before on the channel, often leads to a discrete storm mode, as updrafts are able to move off of the initiating boundary fairly well without interfering with other storms around them. Secondly, the cold front was fairly diffuse with not a very strong temperature gradient across it. You see 80s to low 90s on the east side, 80s to low 90s on the west side. So not a very strong cold front. Often cold fronts will have a lot of cold air on the west side and much warmer air on the east side, meaning that the temperature gradient across the boundary is very strong, and oftentimes that leads to the cold front moving quite quickly, which means a lot of storms initiate along the cold front. And the cold front wasn't moving all that fast, which also tends to limit the amount of convection that can fire along the cold front. Unfortunately, this event occurred a few years before the advent of modern-day WSR-88D radars, so we are only left with fairly primitive radar imagery for this event, but there are some cool things to see from the radars that were scanning that day. This is the King City, Ontario radar located several miles south of Barrie, just north of Toronto. This first image is at 1930Z, so 3:30 p.m. Eastern Time, and you can see the very semi-discrete supercells that we're developing along the frontal zone. You can see kind of the kidney bean shape in some of these storms. And then here we are at 2020Z, so 4:20 p.m. Eastern Time. Once again, kind of a string of pearls, multiple semi-discrete tornadic supercells producing significant tornadoes as they moved off to the east. This was about 40 minutes before the Barrie F4 occurred. Here is a loop from the WSR-74 radar at NWS Pittsburgh, and despite the lack of data quality, this is a really impressive loop. Starting off with the first batch of prefrontal tornadic supercells, you can see clearly the hook echoes and flying eagle shapes of these storms And then the cold front storms come in. Once again, very discrete storm mode, likely a big factor in why this outbreak was able to reach its ceiling. Storms stayed discrete for a very long duration, allowing them to fully take advantage of the environmental parameter space. And again, you can easily pick out the hook echoes in all of these supercells and the flying eagle shapes. Just a classic radar loop showing just how many potent supercells there were in this outbreak. And finally, here is a still reflectivity image from the WSR-74 at Penn State University of the Moshannon State Forest tornadic supercell. Remember, this is the one that produced the F4 that attained a width of over a mile wide for a good chunk of its lengthy path. Just a classic supercell presentation on radar here. You can see the well-defined, very tightly wound hook echo. Overall, just a very, very impressive storm. So that's going to wrap things up for this video. The May 31st, 1985 event remains the most significant outbreak to ever strike the Northeast U.S. and Southern Ontario. And it's clear that a very rare combination of ingredients for this region came together to produce a rash of tornadic supercells, over half of which produced strong to violent tornadoes, numbers that rival even the most intense Great Plains and Southeast outbreaks. With that, thanks for watching, and we'll see you in the next video.